And he will give an overview about the LHEC plans. Please, Kristian, whenever you're ready.
Do you give me the screen free to share, or should I share the screen?
How is it? Can I do this?
I mean, it tells me I cannot share the screen while the other participant is sharing.
Oh, I have no idea how to do this.
Stop sharing. You know, there's a red button.
Yeah, maybe, yes.
Oh, no. Yeah. Okay, try it again. Yes, that works.
Worked.
Can you see now my slides?
You can see your screen, yes.
Okay, perfect. Then I go also to the full screen version. I think, oh, is that? Yep. Okay, so I have the honor to give this talk about the status and plans of the Large Hadron-electron Collider at CERN, and special thanks to Max, who helped me a lot with preparing the talk. So the scenarios we want to discuss here is that we produce an electron beam in an energy recovering LINAC, and if it has a 50 GeV, we throw it onto the proton beam from the high LUMI LHC 7 TeV to get a center of mass energy of 1.2 TeV. And this can be operated synchronously with a LHC operation. And this scenario we call LHEC. The operation in principle could start something around 2035. The cost would be around of the order 1 billion Swiss francs. And the luminosity we might achieve is of the order 10 to the 34 over centimeters squared over second. The other option that we're discussing is that we have an electron recovering LINAC electron beam at 60 GeV and scatter it on top of the proton beam of 50 TeV at the FCC HH. This also can be done synchronously to the FCC operation, of course, and then we would get something like a 3.5 TeV center of mass energy that could operate something like 2050 onwards. The cost would be 1 to 2 billions Swiss francs, and this we would call the FCC EH option. And here you see this energy recovering LINAC in case of the FCC, and here in the LHEC. You see my cursor? Yeah. Okay, I guess so. So then the integrated luminosity. Since we have the energy recovering LINAC is such a nice tool, and also our proton beams from LHC and FCC are so nice, we expect an integrated luminosity of 1 to 2 inverse attobars, which is 3 orders magnitudes more than what we had at HERA. For the FCC, we are actually part of the SCC CDR, physics CDR and accelerator CDR. I give the references here. And for the LHEC, we have written 2 CDRs, one in 2012 and the other one in 2000. And it's actually just accepted by the journal. And last night it was uploaded, we uploaded to the archive. So if you want to see changes for the publication, you can just click on it. Now, this is our CDR, as I just talked about, consisting of 300 authors, and actually 156 institutions are involved, which is, I think, quite a number. However, if you don't want to read the full 400 pages, you can just read this 5-page summary by Oliver Brüning and Max Klein, which is part of the ECFA newsletter number 5. And here I give you also the link. Now, to show you how this project is embedded into the different colliders, so high collider projects at CERN, I want to show you a slide from Jürgen Dont, because I couldn't show it better. Yeah, here's the timeline as a function of the time. So we have LHC, we will have a high luminosity LHC at CERN, which is our current flagship and has an impressive program until 2040. Beyond 2040, we plan to do this big sister future ambition project of building a 100-kilometer ring. And if we fill it with electron-positron beams, then we have the FCC-EE, which will be really a great Higgs factory, and you can do lots of electroweak and top precision measurements. If we fill it with hadrons, then we will have the FCC-HH. And here we have now, as we have for the high luminosity LHC, the option to do electron-proton scattering with the LHEC project, as I've talked to before. Here we have the option to do the FCC-EH option with this FCC-HH collider, and around 2026, somehow we have to verify whether this is a feasible plan or if this is not. So this is well embedded into the current collider programs. It is also part of the European strategy for particle physics. Here you see a very nice talk Ursula Bassler gave at the German Physics Society Spring Conference about this European strategy, and she nicely had talking about also the EP colliders. She also did this plot here, which you probably know already, which is the timeline for future colliders at CERN, China and Japan, which is part of the European strategy. And you see here the LHEC here starting at around 2035 in parallel, operating in parallel to the high luminosity LHC. And FCC-EH could then operate in parallel to the FCC-HH, which is shown here in the mid of the 40s. However, if you would have this option of a high energy LHC, it could also operate synchronously with that. So that is well part of the European strategy. But now let me give you a little bit of overview of the status and the plans. And let me start with these energy recovering LINACs, because at the LHEC and FCC-EH, we need high luminosity and high energy. We really need a high power facility to be used for an energy recovering LINAC. So high power means high currents. So we need high current sources, but we also need high energies, and they should be done with high quality superconducting radio frequency cavities. The first 802 megahertz cavity has been successfully built at JLab. And you see here this quality factor Q naught as a function of the energy gradient. And what we would need for the LHEC is something like 2 times 10 to the 10, and it's actually performing better. So this is really good news. To get high energies, we actually expect the beam to turn a few times around, 3 times around. So the beam will be injected here. Then you have 1 term, 2, 3, 4, 5, and 6, and then it should be at 60 GeV and could be here scattered at the detector. So that gives us the high energy. However, what we also do, if the beam has been scattered, then it will be decelerated, and it will be decelerated 3 times until it's down to the injection energy, which is below the GeV level. And this energy can be given back to the cavities and can accelerate the next beam. So it's a very green accelerated technologies. The power is much smaller than gigawatts, and even the beam dump, since it's decelerated down to the injection energy, is not a big of a problem like in other huge dumps with lots of radioactivity. So we can manage to do that and get something like 60 or 50 GeVs. The small one is if we go down to 50 GeV, which we're currently investigating. We shouldn't go further down because the tunnel is a small part of the cost and should not be reduced further because of the large synchrotron loss, etc. But if we are at 50 GeV, then we would live with 112 cryo modules with 4 cavities each. So total number of cavities of 900. Just to compare, at the EicC, we would need of the order of 10,000. So that's a much smaller project. And I say it will save energy, and it's a green project. And the other thing that is very nice about it, there's lots of technical synergies with other applications. So for example, Vladimir Telnov just gave a talk in March 21 at the Linear Collider workshop that you can operate the EicC as an ERL and boost up the luminosity to 10 to the 36. But there are other projects like Sapphire, a gamma-gamma collider, where you could use ERLs, or you could use it as an injector into FCC-EE. There are studies, you could make an FEL out of it. You could use it as an ejector for FCC-HH. There's also a proposal of an ERL version for FCC-EE for high lumi at high electron energies. Actually, there's also share of technology. This 802 megahertz technology can be shared between parallel FCC-EE and even ESPS. The cryo modules of SPL at 704 megahertz, which are expensive, can actually modify it to be used at parallel. In the Alice gun is actually already delivered in Orsay to use at parallel. The JLab EIC booster is likely to be used at parallel. So lots of collaborations and synergies going on also for forward colorimetry and inner tracker and so on. Now, let me come to this powerful ERL for experiments, which is called PERLE and is supposed to be built at EicC. The collaboration consists of CERN, Cornell, Daresbury, JLab, Liverpool, Novosibirsk, and EicC. And this will be the LHEC technology development facility that can also be used then for high luminosity particle and nuclear particle physics experiment, like you could do high precision elastic EP scattering or photonuclear reactions and so on. And this project is actually part now of the global ERL developments, a part of the roadmap end of 2021. About the synergies to other projects I spoke already, but let me show this ERL landscape by a plot of Chris Tennant. So you see here different projects. In green, those are operational. In orange, they are legacy. In blue, under construction. And in violet, those ones which are proposed as a function of the energy in mega electron volt and as a function of the average current in milliampere. And then these dashed lines give you the power. And you see PERLE is here actually at 500 MeV beam energy, 20 milliampere currency. So you will see it's at the first 10 megawatt ERL facility. And so I think it's a very interesting project. The next steps are nicely summarized in a talk by Alex Bogac. Let me just show you his summary slide here. So what we have to do is to complete the injector design, do end-to-end tracking and validate the design. Magnet specifics and prototyping of the beacon magnets have to be done. Actually, the different HOMs, and HOM was standing for these. Okay, now I'm just thinking about it. What was this HOM again? Just the higher order modes. Yeah, they have to be designed and tested. Then the preparation of the Alice gun, as I talked about, will be installed at EicC. The PERLE TDR is due end of 22, and PERLE needs to be integrated in the European roadmap for accelerators, and then PERLE will become a key part of the future high energy physics, particle physics, and also nuclear physics. Okay, let me now go to the detector design actually. And this is a picture of the detector. It's 13 meters long. The radius is close to 5 meters. Actually, the FCC EH detector is shown a bit smaller. However, it is, of course, bigger. It's 19 meters long and 6 meters in radius. So this looks a bit misleading, but I want to show you in great detail the LHEC detector design. Like typically you have here the inner trackers, and those trackers are complemented with forward and backward spectrometers, mainly for diffractive physics and photoproduction. Then you have the solenoid, and you have the electromagnetic and the hadronic calorimeter and muon detector, and it has been installed or it has been studied how to install it actually in the IP2 cavern, as you see here, some sketch. But let me go a bit more into the detail of this detector design. Let me have a look at the calorimeters, which have now a complete coverage of ±5 in eta pseudo rapidity. In the central region, we used in the 2012 proposal liquid argon. Now it's scintillator ion options in the 2021. And in particular, of course, the forward region is crucial because there we have dense and high energy jets of a few TeV. And in particular, if you want to search for H to BB and other reactions, you really have to have a high resolution. In the backward region in DRS only deposits something like energy below the electron energy. But how this can be accomplished in the different calorimeters is shown here by the different number for the electromagnetic calorimeter, the hadronic calorimeter, forward hadronic, forward electromagnetic, backward electromagnetic, backward hadronic, and you see the different readouts and absorber material, like in this case, scintillator lead, scintillator iron. Here we have silicon tungsten, and you see also the total area of scintillation material for the different detectors, and then we can really achieve and hope to achieve to do, for example, proper H2BB bar reconstruction. Now, this is a design picture of the tracker. The inner tracker rapidity goes up to 5 in eta. R0 is 60 centimeters. The impact resolution 5 to 10 micrometers, and the total square area for the silicon used is 40.7 meters squared, and here you also see the more technical details. Let me also explain or come back to a new idea. I mean, of course, Alice, they wanted to have a new tracker for nuclear physics, and they call it A3. And the idea came up, how could we integrate this A3 detector, as you see it here, and here's the reference, into the LHEC detector. And if I switch back, you see that our calorimeter, whatever, or the tracker ends at 65 centimeters. And if we blow up this a bit to 130, actually then this A3 detector would actually fit. And that would, of course, also help because, you know, we have only one interaction point for both nuclear physics at Alice and for the LHEC as well. And here we could really unify the slim new heavy ion detector A3, which is used for low PT physics, with the LHEC detector and have a combined detector. Now let me come the last few minutes to the physics, and actually, of course, we do deep inelastic physics. And what kind of area we cover at a function of the scale q squared, and x is shown here. We extend to very low x, of course, and this is of course very interesting because it could discover some new QCD or novel QCD dynamics, but we could also go to high x and to high q squared, and then we have enough energy to produce the Higgs boson, the top quark, and probably exotic particles. So it's both that we can do at the high energy frontier if we have EP scattering at the high energy frontier. So these are somehow the things that I think this collider would be really deliver. So it's the cleanest high resolution microscope. Of course, it will empower by the measurements of the PDFs, of course, the LHC FCC search program. But okay, together also with LHC and FCC-HH, it will be a really high precision Higgs facility. And we can do precision measurements and of top and electroweak physics. And we can use these precision measurements to do high sensitive searches for physics beyond. I will show you a few examples in the following. And of course, it's a unique nuclear physics facility. So I really think this is a nice project, and it will be very nice for our diversity of our field to have these electron-proton scatterings. Now, let me start a few highlights of physics. Of course, one highlight is the parton density functions. You see here the expected uncertainties as a function of x, yeah, for up, down, and gluon with low x and gluon with high x. And this dark blue one, this is actually the uncertainty expected at the LHEC. And you see, if you compare different PDFs with that dark blue band, how the errors shrink dramatically. And even in areas which are very interesting, like low x saturation area in the gluon type, or the area where we do Higgs proton-proton physics, like indicated here, or the areas at high X where we do BSM searches at proton-proton. So this is really a dramatic, huge improvement, but also let me remind you that the LHEC also provides a single coherent base for PDF determination to N3 leading order. So this is also, I think, a very important thing. You can also do nuclear physics. Of course, here are now the uncertainties on the PDFs for protons as a function of X. And this the brown one is LHEC, green one is FCC-EH, and black one is the combinations, as you see, of this huge range, the very, very low uncertainties. This is similar for lead. And if we look back in our studies, we will see if we do the ratio over protons over deuterium, for example, or other nuclei, we can study these typical effects like shadowing, anti-shadowing, Fermi motion, the EMC effect, and so on. So let's do that here as well and plot the ratio of lead over protons and see how the uncertainties are. And you see a dramatic small accuracy that can be expected. So here we really learn a lot about nuclear physics as well. Now, one example, or actually two examples for precision measurements in electroweak physics and top quark physics. Here, the example I want to give you, I have an exchange of a Z boson. So this is neutral current, deep and elastic scattering. And with that project, we can measure the couplings, the vector couplings to the up quark, for example, as shown here, versus also the axial vector coupling to the up quark, as shown here. And here you see in green, this was the area of the measurement of H1. This was the one from D0, and this is the expected measurement with the expected accuracy in yellow for the LHEC and the tiny one for FCCEH. So it's very dramatic high precision below the percent level. And this could also be used, since the couplings depend on sine square theta Weinberg. You can also measure this at the per mil level. And this is actually shown here, the relative uncertainty as a function of square root of Q square. And you see over very large range here, you have a very, very low relative uncertainty. So you could even study the scale dependence of sine square theta Weinberg, which is of course great. And you could also extract the W mass in such measurements with an uncertainty of 4.5 MeV, 3.6 MeV alone from the PDFs. And of course, if you do these high precision measurements, you can also turn them into high sensitive searches for new physics. I show you one example here. So here we use these electroweak measurements to search for anomalous operators, for different ones. And we have combined the FCCEH results now with the FCCEE results, also to show you the complementarity and that we really gain if we have all these different colliders. And here you see actually the reach in terms of the scale of the new physics that can be achieved. And in many of those, we can go up to 30 TeV. But the combination of the result is really favorable. So we really love to have both of it. Let me also give you one example for top quark physics. So here we look into, I mean, the LHEC will already be a factory for single top quark production with a very low backgrounds if you look into the leptonic decays of the top quark. And this will be by charged current exchange of the W boson. And then, of course, you have here the WTB vertex in the initial state, and you can measure VTB basically independently of any models. Of models like the unitarity of the CKM matrix that you might want to use. You don't need it here. You don't need to make assumptions on the numbers of the quark generations and such like this. You can just measure it, and you can measure it with a very high precision already at 100 inverse femtobarns. After 1 year of running, you could measure VTB with a very high precision of on the percent level. And this is compared now to the current measurements of VTB at the LHC. So it's a high precision measurement, and you could also perform, which I cannot show you here, high precision measurements of VTD and VTS. Now let me come to the Higgs physics actually. And Higgs physics will show up already in the first 100 inverse femtobarns of data as a bump in the distribution after 1 year of data taking, as was discussed, investigated in great detail here. Of course, at the LHEC, we are dominated by Higgs production via WW fusion and then Higgs to BB bar decays, while at the LH future E plus and minus collider, you are dominated by Z Higgs radiation of a Z boson, so that you have Z Higgs production. And if you look what are the expected accuracies of the different Higgs couplings in the kappa framework, you will see, of course, that the LHEC gets best prediction here in brown. These are the predictions for LHEC for WW Higgs coupling, but the E plus and minus collider for the ZZ Higgs coupling. And if you combine the results, like the green one here is ILC plus LHEC, and if you combine it even with PP, you get the blue results, then you will get also a dramatic increase. But it's nicely to see the complementarity of those different colliders. Let me also show you one other example. If you compare EP to PP, then we will get actually the dark brown blue one is the high luminosity LHC alone. If you combine it with EP, you get the lighter blue one for the different couplings to the Higgs boson. And in green, this is the ILC at 250. And you see in many couplings, BB, WW, GLU, tau, tau, and also gamma, gamma, this combination of EP and PP is superior in the accuracy. However, it's really nice to see that the LHEC together with the high Lumi LHC will turn into high precision Higgs facility with measurements of the couplings below 1% in most of the cases. Now, and this is the last thing I want to show, searches for new phenomena. There are tons of searches for new phenomena like lepton flavor violation, exchange of heavy scalars and vector particles. That's it's a hot topic. Here we have search for heavy scalar, which then decays, and you have lifetime effects and many, many more. Oliver gave a nice talk about it yesterday. I want to cover something he hasn't covered actually yesterday, but which I really like it. And since the conference hadn't been taking place in 2020, you haven't seen it, his final results. So this is a search for lepton flavor violation in the neutrino sector. So this is very interesting, of course, since we know that the neutrinos have now a non-vanishing mass, and you can search for sterile neutrinos, for example, in a charged current scattering at an EP collider. And then the sterile neutrino can decay into a lepton and a W boson. And this angle theta is actually the sterile mixing angle. And then the W boson can decay into two jets. And you can now set limits on this mixing parameter as a function of the sterile neutrino mass. And this is shown here in blue for the LHEC and in red for the FCC-EH. And you can compare this to different colliders. This is Delphi, Atlas, and the MEG is the muon gamma, mu to E gamma experiment. That's this green one here. However, if you go to lower masses of the sterile neutrino, then you will see lifetime effects, and then you get these limits here, which are also extend on existing limits. Now, and this is the final thing I want to show, let me compare this to the different new colliders or future colliders that we look at, and this shows how nicely complementary these different options are. So these are now the limits on this mixing parameter as a function of the sterile neutrino mass for the different colliders. Here is FCC-EE, and you see this dominates at low values of the sterile neutrino mass. At high values, we are dominated by the measurements or the projected measurement of FCC-EH, and in the middle area there, the FCC-HH has the best things to say. So it's really nice to have these three different collider options, and it's very nicely and for the complementarity. So as conclusions, let me just show you what the actually International Advisory Committee has sent to the Director General. And you haven't seen it because it's from end of the year 2019 and we didn't have the conference this year. So that would be also then the conclusions I want to give you. So the installation operation of the LHEC has demonstrated to be commensurate with a currently projected high luminosity LHC program, while the FCC-EH has been integrated into the FCC vision. The feasibility of the project as far as the accelerator issues and detectors are concerned has been shown. The sensitivity for discoveries of new physics is comparable and in some cases superior to other projects. The addition of EP and AEA experiment to an LHC substantially reinforces the physics program of the facility, especially to areas of QCD, precision Higgs and electroweak, and as well heavy ion physics. The operation of an LHEC and FCC-EH is compatible with simultaneous PP operation, which is important to state. Many people still don't know that, because the LHEC at the interaction point 2 would be the appropriate choice. Actually, the development of these ERL techniques are very interesting and intensified in Europe in national laboratories, but with the collaboration of CERN, and this preparatory phase will be necessary. This is parallel what we do already. The recommendations is that it is recommended to further develop the ERL-based EPA scattering plans, both at LHC and FCC, as an attractive option for the mid and long-term program of CERN, respectively. Before decision on such a project can be taken, further development work is necessary and should be supported, possibly within the existing CERN framework. The development of the promising high-power beam recovery technology ERL should be intensified in Europe. CERN should participate, which they have done. They are part of the PERLE collaboration, and it is recommended to keep the LHEC option open until further decisions have been taken, and investigation should be started on the compatibility between LHEC and a new heavy ion experiment. And this is what I said, these discussions of integrating the A3 detector into LHEC. So I think this is an exciting program. We are continue to work on it and to shape this future. It is already well established, the beginnings, but there's a lot to come. And let me just finalize with something out of Back to the Future. Doc Brown says, our future hasn't been written yet. Our future is whatever we make it. So let's make it a good one. And I would like to add, let's make it a diverse one, and let's have all these different collider options. That would be, of course, great to have.
Thank you.
Thank you.
Okay. All right. So we have maybe time for one quick question from the audience. Saleh. Please go ahead, unmute.
Kristian, thank you very much for a very nice presentation. I have one comment really, not question, but this comment, in my opinion, is very important. Comment is following. We can consider 60 GeV, but now 50 GeV energy recovery Lene as a baseline option for Large Hadron Collider, based lepton hadron colliders. In my opinion, it should not be sole option, but as baseline it is okay. But it cannot be the sole option for FCC-based colliders. I think that we should not restrict ourselves with 50 GeV energy recovery Lene as the option, sole option for the FCC-based lepton hadron collider. We should consider other possible alternatives, including energy frontier options, including muon proton, really something like EicC cross FCC, etc.
Yeah, we use usually in the CDR, we use 60 GeV, but I think you probably think that we should go beyond that, of course. Thank you for the comment.
Thank you.
All right, thank you very much, Kristian, for the nice review.
Thank you.
Okay, so we don't have much time for new questions because we are going over time, but
I was over time, I'm sorry.
Okay. I had a few questions myself, maybe offline.
Okay.
So next speaker is, if you can share the screen, next speaker is Ruth Jacobs, and it's also about LUXE and new experiment to study non-perturbative QED in E-laser and gamma laser collisions. Please go ahead.
Okay, you should be able to see my screen and also now in full. Okay, let's get started. Yes, hi, I'm happy to report on the LUXE experiment, which is a new experiment to study non-perturbative QED. Oh, it says my share was stopped. Can you still see my screen?
Yes, perfectly.
Ah, okay, sorry.
No longer. Now we see you.
No longer? Okay, sorry.
Okay, yeah.
Now it should work, right? Perfect. So LUXE is a proposed new experiment at DESY in Hamburg in Germany, and it is using the electron beam of the European XFEL, which is the X-ray free electron laser close to DESY. So LUXE will study collisions of the XFEL electron beam and a high power laser. As you can see in this sketch, I've given you a map of the local area around DESY, where you can see the DESY campus on the bottom right, and you can see the XFEL outlined in red, and you can see where the LUXE experiment and the electron laser collisions will happen at the end of the electron accelerator of the XFEL. So LUXE is a synergetical project between particle physics and laser physics, and we are a growing international collaboration with about 90 members from 26 institutes. And we've just released our conceptual design report, and you can find a link to the archive here and also a link to our website. So as an introduction, many of you know, probably all of you know, that QED is one of the most well-tested theories that we have in physics. And most of these, or almost all of these tests of QED are based on perturbative calculations. And with LUXE, we propose to study QED in a new and an uncharted regime, which is called the strong field regime. And when we say strong here, we mean that the work by an external field done over a Compton wavelength is actually larger than the rest mass of a virtual particle. And this is called the Schwinger limit. It goes back to work done by Julian Schwinger. And what happens if we go to these very strong fields is that if we consider virtual particle loops and we apply our external field that is that large above the Schwinger limit, our virtual particle loops actually split, and we could create a real particle pair. So in the case of QED, this means an electron-positron pair. So as you can see, if you have a perturbative calculation that is based on loops, this will no longer work in the Schwinger regime. So our QED really becomes non-perturbative above the Schwinger limit. And to give you a feel for what the Schwinger limit is, the critical field that reaches this non-perturbativity, you can find if you do dimensional analysis. And if you write this down for an electrical field, you would get a value of 1.3 times 10 to the 18 volts per meter. So this is a really, really high field that you have to apply. Places in the universe where we have really, really high fields, and this is an exciting analogy to this effect, is actually black holes. Where the Schwinger field is actually not an electromagnetic field, but a gravitational field. And what happens there is then that you have these virtual particle loops splitting into particle-antiparticle pairs, where one falls into the black hole and the other one escapes the event horizon. And this is nothing else than Hawking radiation. So LUXE, in a way, can be seen as the electromagnetical analogy to studying Hawking radiation in the lab. So how do we do this? How do we study strong field QED? I've already mentioned we're looking at collisions between electron beam and a laser. So we start out with our electron beam going here from the left. And these are high energy electrons of 16.5 GeV from the XFEL beam. Then here in the picture from the right, we have our high intensity laser pulse. This is an optical laser at terawatt intensity, 800 nanometers wavelength. And this already gives us a large electric field. However, by itself, this field is not large enough yet to reach the Schwinger limit. But what helps us here is that we have these high energy electrons, which are Lorentz boosted. So the electrons, in fact, see a larger E field of the laser in their rest frame because they're boosted. And you can see the effective energy here, and you can see this gamma factor in here. And due to the 16.5 GeV, this gamma factor is 10 to the 4. So the electrons in their rest frame see a huge laser field above the Schwinger limit. And then we have the interaction between the electron and the laser, and we produce our real electron and positron pair. And the physics processes that happen here are two in the electron plus laser collision case. So the first one is nonlinear Compton scattering, which you see here as process one, where our electron is coming in and it is absorbing, it is nonlinear, it is absorbing multiple laser photons, and then is emitting a Compton photon and this Compton scattered electron. And then the second process that happens is that the Compton photon produced in this first process absorbs itself, again, multiple laser photons, and then produces the electron-positron pair, and this is called nonlinear Bright-Wheeler pair production. So the main goal of LUXE is really to measure the positron rate coming out of the Bright-Wheeler pair production as a function of the incoming laser intensity. The second mode with which LUXE is proposed to be run is the photon plus laser collisions. So here we start out exactly the same with the high energy electrons and our high intensity laser, but what changes is that we insert a target in the high energy electron beam where the electrons produce Bremsstrahlung photons in the GeV energy regime. And then these Bremsstrahlung photons interact with the high intensity laser beam, and again, electron-positron pair production happens. So the physics process that takes place here is only the nonlinear Bright-Wheeler pair production, where the Bremsstrahlung photon comes in, absorbs multiple laser photons, and produces the electron-positron particle pair. And LUXE is the first strong field QED experiment to probe directly the photon-photon interaction with externally produced GeV photons. So let me say a few words about the laser. This is an integral part of LUXE. As I've already mentioned, that this is an optical laser. The active medium is titanium sapphire. The wavelength is 800 nanometers. Here on the top right, you can again see the laser interaction as a sketch. So you can see that in the actual setup, the laser will come in at an angle and will be focused into the electron beam. So the laser intensity, I've given you this expression here, is inversely proportional to the pulse length and also to the laser spot size. So actually the spot size will be used in LUXE to vary the laser intensity. So you can see here that the spot size will be larger than 3 microns. So this will actually be a parameter that can be varied to get varying intensities. So as for the power, for the initial stage of LUXE, an existing laser configuration called the JETI-40 laser will be used. This laser comes from Jena. It has 40 terawatts, but there is an option to upgrade this to 350 terawatts for the LUXE phase 1. So as I've already mentioned, thanks to the electron boost in terms of the laser, we don't really need to push the current limits or state of the art in terms of intensity. But what is very important for LUXE is the need for an exceptional shot-to-shot stability. And this is being ensured by multiple laser monitoring and laser feedback loops. So then let's move further downstream. So I've talked about the interaction between the electron beam and the laser. Now we want to talk about how do we detect the particles that we create. And I've mentioned that what we're mostly interested in is the positrons, but however, we also want to detect the Compton electrons and also the Compton photons. So for the charged particles, the idea is to measure the fluxes in the spectra using a dipole spectrometer. And the challenge here is really that the particle fluxes vary quite widely. You can see this, I've indicated this in the sketch. So the positrons come in a large variation of rates depending on the laser intensity at the interaction point. So this can be 10 to the -3 to 10 to the 4 positrons per shot. The Compton electrons come at an abundant rate of 10 to the 9 electrons, and also the Compton photons are very abundant, 10 to the 9 photons. So we really need to adapt the technologies in LUXE to the respective fluxes of our signal, and of course also of our background. Slide 8 shows a CAD model of the electron and positron detectors. So these are the detectors placed immediately after the interaction region, after the dipole magnet. Here in this slide, in the sketch, you would have the electrons, positrons, and the photons coming from the interaction regions here from the right. The dipole magnet would be here, but it isn't shown. And the positrons would be deflected coming out of the screen. The electrons would be deflected going into the screen. And you can see the different detector technologies that we have. So for the positrons, which have a relatively low rate, we foresee a silicon pixel tracker with 3 layers. And this uses the pixel technology Alpide that was developed for the ALICE detector upgrade. And then furthermore, after this, we place a high granularity electromagnetic calorimeter, which provides an independent energy measurement on top of the dipole spectrometer. On the other side, on the electron side, as I've mentioned, we have this huge rate of electrons, 10 to the 9 per shot. So we need to have detectors that can deal with such a huge rate of particles. And there we foresee a gaseous segmented Cherenkov detector that will provide a position measurement and a scintillator screen where the scintillation light will be captured by an optical camera. And then from here downstream, the photons would be detected in a dedicated photon spectrometer. So you already saw that for each side of the detector, we foresee 2 complementary detector technologies. This is to cross-calibrate and also to, in the end, reduce our systematic uncertainties. So let's come to what we actually expect from LUXE. So these are our predictions from strong field QED and our expected results at the same time. This is a very busy plot, so let me talk you through it very slowly. First of all, what is on the axes? So in the x-axis, we have the intensity parameter Xi. This is a measure of the power or of the energy transferred by the laser field to a probe particle. But at the same time, this is a parameter that parameterizes the nonlinearity. So if Xi is above 1, we're entering the non-perturbative regime. Then on the x-axis on top, we have the so-called quantum parameter. This is also a nonlinearity parameter, but this quantifies mainly how important are quantum corrections to the effects that we observe. And then on the y-axis, we have the probability to observe the Bright-Wheeler process, the Bright-Wheeler process being the electron-positron pair production that we mentioned initially. So I would like you to focus mainly on the lines near the 16.5 GeV box. These are just varying the electron beam energy going in. So we foresee 16.5 from the XFEL. So first of all, we have this dashed blue line, which is the perturbative prediction. And this is according to a power law, as you can see here. So if Xi is much smaller than 1, the positron rate will accord to this power law in the perturbative regime. And then you can see these green dots, which is the prediction for full plane wave QED. And you can see that the further we approach 1, and as we go above 1, these green, the green dots start to deviate from the perturbative prediction. And this is exactly what we want to measure with LUXE. So these green dots, they behave according to this exponential function with this quantum parameter that we've mentioned. So the aim of LUXE is really to see the departure from the non-perturbative regime, the departure from the power law, and we want to extract also this coefficient quantum parameter chi gamma. So to place LUXE a little bit within the strong field QED parameter space and also within history, on the left-hand side, we show LUXE in this grid of intensity parameter xi and quantum parameter chi. You can see the different configurations. So the dots correspond to different laser powers and different spot sizes. The blue dashed lines correspond again to different beam energies. And then you can see here a couple of other selected experiments. One I wanted to highlight is the E144, which was an experiment at SLUC in the 1990s using about a 46 GeV electron beam. And they reached parameters still below the chi = 1, but they observed this nonlinear Compton scattering and pair production process for the first time, and they observed actually the start of this xi to the 2n power law that I mentioned before. But as you can see, LUXE has really a good chance with these parameters that we foresee to be the first to enter the xi larger than 1 and chi larger than 1 regime that really constitutes the Schwinger regime. And as I've also mentioned, this is the first proposal to directly study collisions between laser and real GeV externally created photons. And then on the right-hand side, you can just again see the parameter space in terms of perturbativity that LUXE will cover. So we will really go from this xi to the 2n part up to the fully non-perturbative regime. So finally, as a bit of a bonus, we've covered the non-perturbative QED part, but as a side effect, LUXE will actually produce a very high intensity photon beam. I've mentioned that we will have a nonlinear Compton scattering of the electron beam with the laser. And so this actually produces an abundant rate of photons, as I've mentioned. And sort of as a parasitic run mode, in LUXE, we can dump this photon beam on a dump at the end of the setup, where actually this high intensity photon beam can create axion-like particles or milli-charged particles via the Primakov process, which then, for example, decay to 2 photons. So if we place a photon detector at the end of the setup, we could have sensitivity to axion-like particles. And studies have shown that the sensitivity could actually be competitive with other experiments that are ongoing and are in planning for this axion-like particle search. So this is like a bonus to the QED program of LUXE. And with this, I would like to conclude. So as I've mentioned, LUXE will explore strong field QED in its uncharted regime. We want to observe the transition from perturbative to non-perturbative regime and directly observe the pair production from real photons. Parasitically, we can search for beyond the standard model physics with the setup. The goal is to install the LUXE setup in 2024 because there will be an extended shutdown plan for the European XFEL. We've just released our conceptual design report. We foresee a set of very diverse detector technologies that are optimized for our physics aims, and the reviews are starting now. So this is really exciting times for us. We're poised and really looking forward to go ahead. So please stay tuned. Thank you.
Hey, thank you very much, Ruth. Question for Ruth from the audience. Saleh, you have the raised hand. Is it from before you need to ask a question? It's like no. Billy?
Hello, this is Bill. Can you hear me?
Yes, we can hear you.
Very nice talk. I just saw a question regarding your gas Cherenkov that you have shown. So considering it's rectangular And you said it's gas, so it only can be one type of gas. Are you only filling it with a heavy gas and looking at particle separation under 3 GeV?
So actually, we foresee to fill it just with a single gas, yes, with actually with argon. Since we have such a large particle rate, we're actually worried about having too much Cherenkov light. Really, we chose argon because it has a relatively low refractive index. So otherwise, we would really swamp our photodetectors with too much light.
I see. So the purpose of this is to do E-pi separation, I assume.
Now, the purpose of this is really to do particle rate measurements. So the Cherenkov light is, or the amount of Cherenkov light produced is proportional to the incoming charged particle rate. And since it's segmented, you can measure the rate as a function of position, which due to the dipole magnet gives you an energy spectrum. This is the idea.
Okay, thank you.
Other questions for Ruth? I actually have one myself. If you go down to that busy plot that you showed till the near the end, this one. So guide my understanding a little bit here on what you expect. So do you have actually any uncertainty on these perturbative predictions or theory predictions in general, and what is the actual precision that you expect to measure there to see what kind of impact basically you expect from your experiment?
So one of the biggest uncertainties that we expect here is actually on the intensity parameter Xi. And this, of course, due to this behavior, also influences us quite a bit. So
so basically, those lines are, it's just a pure prediction that you cannot really turn into a band, let's say, to say like we know between here to there.
So I think there are theoretical uncertainties on these approximations, for example. I can't comment on the top of my head on the exact size. I don't know if somebody is connected who knows this better than me.
All right, thank you anyway. So it's just to help us understanding what is the impact, but yeah. Okay, thank you, Ruth, again. Very nice talk.
Thank you.
So next speaker is Murat Ali Guler, and he will talk about studies of neutrino production with nuclear emulsion at the CERN-SPS. Please go ahead whenever you're ready.
Hello, do you hear me?
Yes, we can.
All right, so thank you very much for giving me this opportunity. I would like to report this Tau project, which was proposed to study neutrino production with nuclear emulsion at CERN-SPS. And as you know, the tau neutrino is the least known particle of standard model. Only a few experiments reported tau neutrino interactions with limited statistics. The donut was the first experiment to observe the tau neutrino interactions. It was the beam dump experiment, and the tau neutrinos mainly come from the DS decays. On the other hand, Opera, Super K, and the EicC detected tau neutrino interactions. However, the tau neutrino mainly come from the oscillations. And the cross-section of the tau neutrino interactions measured in a donut experiment with a large systematic uncertainty, larger than 50%, and it mainly comes from the neutral flux prediction. Indeed, donut reported the cross-section as a function of the parameter n, which is responsible for the differential production cross-section of the D sub s. Therefore, the central value of the cross-section was not defined, as you see here, no central value reported. And the cross-section can be calculated only if donut use the parameter value derived from the PTA, which is this 6.1. Note that this parameter value is significantly different in the recent version of the PTA. So the aim actually is now to lower this uncertainty to 10%. And also the precise measurement of the tau flux is also important for the important input for the coming the future neutrino experiments shape dune at the hyper K. And also the first measurement of the sub S differential cross section will be performed, and we will have a lot of charm pairs, and we can study the intrinsic charm component in proton. And what we are looking actually this peculiar double King topology, that is the DS decays into the tau lepton with a mean flight length of the 3.3 millimeter, and the tau lepton decays with a mean flight depth of 2 millimeter. In addition, we have the charm quarks. Charm quarks are created as pairs, so another decay of the charge or neutral charm particle will be observed with a flight length of the 5 millimeters. So the aim is to collect the about 1 kilo d sub s decays in 2.3 times 10 to the 8 proton interactions in the target. This measurement has a technical challenge. First, all the decays, as you see here, take place at a scale of millimeters. And the second, the King angle of the DS to tau lepton is anticipated to be very small. It's 7 milliradian. So to detect this topology, we use the emulsion particle detector that provides the best spatial resolution among all particle tracking detectors. Emulsion detectors and the automated readout system have been successfully employed by several neutrino experiments, such as Chorus Donut and the Opera experiments in past. The emulsion compromise a number of silver bromide crystals, which are semiconductors with a band gap of 2.5 electron volt dispersed in the gelatin. And the diameter of these crystals is like 200 nanometer. So once the charged particle passes through, the ionization is recorded quasi-permanently, and then they amplified and fixed by the chemical processes. And as an example of the one interaction in nuclear emulsion, you can see here the pion interaction. You see that you can clearly see the pion interaction vertex, and also the particle bunch of particle emerge from this interaction point. So it provides actually 3-dimensional tracking detector, and the tracking intrinsic resolution is like 35 nanometer. All right, so you see here the schematic view of the emulsion detector that we plan to use in DS tau. You see here this is the basic unit. It has the 100 micrometer thick tungsten target. Is followed by the 10 emulsion films interleaved with a 200 micrometer, this gray level, plastic sheets, which act as a decay volume for the short particles. This unit structure is repeated 10 times to construct the one module. And the ECC emulsion cloud chamber follow this structure. And this part is used to measure the charged particle momentum by means of the multiple Coulomb scattering. And indeed, to have the uniform distribution or irradiation on the detector module, these detector modules are mounted on a stage we call the target mover, and it is synchronized with the SPS CPS. All right, so the emulsion experiments or the emulsion technology requires a second data acquisition. This is the emulsion scanning. It is performed by the high speed and the high precision microscope, which are improved recently and become available. And the emulsion readout can operate at a track density up to the 10 to the 6 particles per centimeter square. And you see also that the speed of the present version of the system is 9,000 centimeters square per hour. So we performed this scanning in 2 steps. In the first step, we actually do a fast scanning to tag this tau decays. It has the decaying angle order of 100 milliradian, so it is easy to tag. Once this decay is located, then we search for this D sub S decay and doing a second phase of emulsion data acquisition, and this will be done with a piezo-based high precision Z axis, allowing the measurement of the hits in the emulsion with nanometric resolution, say. All right, so we can achieve the angular resolution of 0.3 milliradian in this second phase of this precise measurement. Concerning the signal and the background topologies, signal topologies are very unique. All the decays take place at a scale of millimeters, and the King angle of the DS to tau lepton is very small, and we have also the second charm decay charge, or the neutral. The background topology mainly due to the hadron interactions. If you do not identify these nuclear fragments, that interactions mimic these decay topologies. But at this precise measurement, the second phase of scanning will actually suppress this background. All right, then we have actually estimated our efficiency considering the 4 main parameters: flight length and the King angles. And following this selection criteria, we have estimated our detection efficiency as 20%. We need also the momentum of D sub S, and this will be momentum will be reconstructed by means of the machine learning algorithm using these topological variables, the flight lengths and the King angles. Those are proportional and inversely proportional to the gamma factor of decaying particles. Then the combination of these 4 variables effectively provide the estimate of the D sub S momentum. And then the Monte Carlo simulation based on PT actually gives us like 18-20% resolution, and doing the fit the exact parameter, we actually get the 400 GeV proton case, the N parameter 5.8. All right, then concerning the data analysis, actually we performed a pilot run in 2018. And the emulsion readout was completed, and we are actually doing the data reconstruction and the data analysis. And based on the subsample, we have observed like 115 double decay topology, which is quite consistent with the expected number of signal in the background. With this limited statistics, actually, we have done also a data Monte Carlo comparison of the flight lengths, say that the charge prong and the neutral prong case. So we plan to actually complete the analysis in 2021, and we expect like 80 D sub S decay, and this will actually reduce the uncertainty on the new tau flux to 30%. About this event reconstruction, the tracking efficiency actually is more than, say, 95%, and the alignment accuracy is like 0.4 micrometer in position and 0.1 milliradian in angle. And also the vertex distribution looks very consistent. And this is the one event we have observed, and this event actually you see here, we start with the high density track environment. It is like 4,000 tracks in 2 × 2 millimeters square. And then we actually, from this density, we can identify the proton interaction. and also successfully locate the decay topologies, right? Then this is one of the candidate event. It has the V topology and the King topology, and the King has the flight length of the 2.5 millimeter, and the V has the 0.5 millimeter. The King angle is about 120 millirad. All right, then about the physics runs, and it is scheduled in 2021 and 2022, and the beam time is allocated in October in 2 weeks, and also it will be 2 weeks in 2022, and we will plan to produce 150 meter square emulsion and the tungsten targets. And after the 2021-2022, we plan to reach the precision of 0.4 for the N value. And the emulsion production is going on in Nagoya University. We have this film production facility, and this well, since the amount of emulsion is quite large, it will take the few months to produce the all emulsions, but will be ready before the October. All right, about the collaboration, and you see that the collaboration includes the groups from the 5 countries, and we submitted the letter of intent in 2016, then conducted 2 test beams in 2016 and 17, and submitted proposal in 2017, and we had the pilot run 2018, and finally the experiment approved in 2019, and the physics run scheduled in 2021 and 2022. And my final words, the Zhao project actually is proposed to measure the neutral flux production cross-section, and the aim to reduce the uncertainty from 50% to the 10%, the uncertainty in the cross-section measurement. And we used the emulsion detector with a nano precision readout. And also we would have say that about 100 kilo charm events that we can actually do the a lot of charm studies. Indeed, that's also the analysis of the pilot run is going on. Thank you for your attention.
Thank you very much. Okay, as usual, questions orally. We don't see any hands rising. Okay, must have been very clear talk. So thank you very much again for giving this presentation. So next speaker is Yuxiang Zhao that will talk about the electron-ion collider in China. Whenever you're ready.
Okay. Yeah. Can you hear me?
Yes.
So let me put it on. Do you see my screen?
Yes, we can. Can you do it like full size screen?
Yeah. I'm doing it. Okay. Now it's on full screen.
Perfect. Thank you.
Okay. So thank you for the opportunity to give introduction on the electron-ion collider in China. And in the following a few slides, I'm going to talk about the electron-ion collider in China in general, and then mention about a few physics highlights, and then talk about project status, and then come to the summary. Before we talk about the electron-ion collider in China, there is another facility called HIAF. We want to mention it. And if you look at the map of China, HIAF is located here in the south part of China. It's here, if you zoom the map, and you can see in the Guangdong province, and it is located in the city called Huizhou. And on top here, you can see the landscape of the here facilities under construction, and the bottom one gives you an idea on what will it look like in the future when it is done. And so the facility, this is a layout of the accelerator facility. The total investment is about 2.5 billion Chinese yuan, and is fully supported already. and you can see the accelerator, the injector part, the lean neck, booster ring, as well as the storage ring, and also some experimental halls for atomic physics and nuclear physics, applied research in biology and material science. And based on this facility, we will build the electron ion collider in China. This is our logo. And by using different color, you can see where is E and I, also collider C and China in red color. And then the arrow here means polarization. Recently, we released our white paper on archive, and it is also accepted by the journal Frontier of Physics, and it is in production stage. And for this EICC collaboration, now we have 46 institutes and more than 100 physicists working on it. For the EICC accelerator complex layout, the part marked within this dashed area is the here of facility and also accelerator under construction. And the maximum beam energy for the proton is around 9 GeV. So to build the EICC, we need to do upgrade for the proton or ion accelerator to this H-shaped style ion beam with beam energy around 20 GeV. And in addition, we will build a new electron accelerator, including electron injector and the storage ring. And the beam energy is around 2.8 GeV to 5 GeV. So this is the complex. A few specs for EICC. The left plot shows you the luminosity as a function of central mass energy for the worldwide accelerator facility. And you can see the EICC is here, and also the US EIC is here. And the right plot shows you the Q square versus X coverage for JLab 12 GeV EICC using 3.5 GeV times 20 GeV as example, and also the US EIC using 10 GeV as 100 GeV as example. You can see the Q square versus X coverage. And we want to emphasize that the EICC covers the kinematic region between JLab experiments and the US EIC. And it also complements the ongoing scientific programs at JLab and the future EIC project. And we will focus on moderate X and the C-quark dominated region. Then in the following few pages, I will show you the physics highlights. Now we have the following four physics highlights, like a spin structure of the nucleon, including a 1D structure and a 3D imaging. And this requires a polarized electron and the polarized proton and light nuclear beam. And then the second topic is the platonic structure of the nuclei and the proton interaction with the nuclear environment. This we will use unpolarized electron beam colliding with unpolarized various nuclei beam. And we will also do extensive studies at the EICC on exotic states with the CC bar and the BB bar. This has some historical reason because we have BAS3 experiment in China, in Beijing. And then the last topic is the origin of the proton mass study via heavy quark-helium near threshold production. So in the following, I'm not going to cover all of them, but we'll give you some examples. The first example is about the spin structure of the nucleon, the 1D case, the helicity distribution. And by including the EP collision and the E-helium-3 collision as effective electron-neutron collision, and also include the CDS processes. And we can do a very good job on the flavor separations of different helicity distributions. And the top three plots just give you an example of delta U bar, delta D bar, and delta S. And then the green hash band shows you the impact of EICC CDS data on top of DSSV 14. And you can see these C quarks can be constrained in a very good way. And for comparison for to the US EIC, you can see in the moderate X region and large X region, in the high energy machine that the US EIC have limited constraints on these C quarks, and this is exactly in the coverage of the EICC. For the 3D imaging, this is an example of the TMD study by looking at the CDS process, again, including the EP collision and the helium-3 collision as an effective neutron process. We can separate the different flavors for U quark, D quark, and S quark TMDs. And for U quark and D quark in this plot, you can see the light green band is the existing precision of what data, and the red band, which is very tiny here, shows the statistical uncertainty, including the 50 inverse Finderbar of EP collision and the 50 inverse Finderbar of E helium-3 collision. And then the blue band is including the systematic error. And at the EICC, it allows maybe for the first time to look at the strange quark TMDs. This is a Sieverts function in these three plots. For the another 3D imaging is about the GPDs, and by looking at the DVCS process or the DVMP with the vector meson production, you can do various asymmetry measurements because of the doubly polarized beam available at the EICC. And here just to give you some examples of less mutual angular dependent asymmetries, and using only one of them, and we feed into a global data feed with some model, of course. In the current stage, we can see the impact of EICC data comparing to the existing uncertainties for various competent form factors. And also, we have ongoing effort collaborating with the Partons group to look at the competent form factor impact using the reweighting method. Another example is the nuclear PDF study with the ion beam. And here again, an example on the U-bar distribution. The left side is the U-bar distribution as a function of Bjorken X. And with EICC data, just a few hours of running, you can see the error bar is shrink. You can already see the effect as can be shown on the right plot, and this is a relative uncertainty. The gray band is the existing uncertainty, and the light blue band is just including a few hours of running. You can clearly see the improvement. The reason why we include a few hours of running of data, because we use reweighting to look at the PDF impact. If we include more data set inside, the reweighting method just failed. So this is a compensation. We just use a few hours of data to look at the impact, to demonstrate how powerful EICC data will be in constraining the nuclear PDF. Another topic is about the proton mass study. The Xiangdongji proposed this mass decomposition to 4 terms: the quark energy part, the quark mass part, and gluon energy part, and trace anomaly part. Also, nowadays people are calling it quantum anomaly. And for the first 3 items, we can constrain PDFs to constrain the quark energy and also the gluon energy. And where pi n, low energy scattering, we can constrain the quark mass. But the rest piece is the trace anomaly or quantum anomaly. And nowadays, people propose to do this kind of study via threshold production of Jeb psi or option. And on the right plot here, you can see the many theoretical calculations as well as the existing world data here in the high W region, and the EICC coverage is within this yellow band. So you can at the EICC we can look at the option production right in this rising near threshold region. So it will give us a good opportunity to look at the option near threshold production, so that we can learn something about the trace anomaly. So about the project status, now we have like a Strawman detector setup for EICC, and now what we're doing is to add in the detector one by one in the full John force simulation. So the John force first John force simulation is basically ongoing, and we will repeat the yellow report like activity to see the impact on various physics topics. And for the detector R&D, is ongoing in parallel to the full John force simulation. We have built clean rooms of ISO 6 and ISO 7 in total of about 200 meters square for detector assembly. And for the pixel detector, we are mainly on the ITS2 or MAPS technology. And here in the picture, you can see the two modules. This is exactly the size of Ali's module for the in the vortex detector. For MPGD tracking detector, we are working on micromegas and also GEM. For the small modules, there is no difficult to do the mass production in China, and our goal is at a large area. For example, for micromegas, we're working on the 0.5 meter times the 0.5 meter scale, and for the GEM, we're working on the 1 meter times the 0.5 meter scale. And this is about a module in the end cap disk detector. At the same time, we have expertise on STGC detector. One of the universities, Central University, is working on the mass production of the STAR experiment. So the R&D of this detector is still is also ongoing. And for the calorimeter, we're working on the Shashnik design and also a tungsten powder style ECAL detector. And the other detectors like Dirk and Rich detectors will, the R&D activity will be followed in the following months or years as the EicC project is moving forward. Regarding the timeline, so we're here, and this timeline is just our hope, and or you can also call it technology-driven schedule, because it's really depending on the funding we got for the EicC project. And the here construction will be finished in 2023, and then at the same time, EicC R&D for detector also accelerator is ongoing. So we plan to do the construction until 2031, and afterwards it's in operation. As I said, this is technology-driven schedule. It's depending on the funding we get for the project. So come to the summary, I have given a brief introduction on the EicC project, and it focuses on the C-quark gluon related study at moderate and large X region, and it can also help to tackle the issue of trace anomaly contribution to the proton mass at the optimal threshold. And at the same time, the more physics topics are under study and development. John force simulation and detector R&Ds are ongoing, and we want to emphasize that the EicC complements the EIC project at a higher energy, and we want more and more people to join. So thank you, and you are more than welcome to join us. Thank you.
Thank you very much, Yuxiang. So questions for our speaker? If waiting for the audience, I have actually a couple. So you mentioned actually the simulation of one detector, but you showed two interaction regions. So you plan for actually to have one detector, or you may envision having two, or what is the plan there?
Okay, so the IR, we have reserved the two IRs, but because of the resource we have, now we are fully working on the first IP. And the second IP will be reserved for new ideas. That's in this. Yeah.
Okay, thank you. Another question I have, if you go to slide 14, help me understanding this impact on the nuclear PDF.
Okay.
Slide 13, yeah, this one. So you are actually here doing the reweighting, right? So this is why you have a slight discrepancy in these two lines, the gray and the blue. And on the right, you show actually a dramatic suppression of the uncertainty down to basically nothing. And this is also true in the region where you don't cover with data. So I'm quite puzzled what I'm reading here.
This is a big question. This is a very good question. So we suspect that's the reason why we mark this hash area is because that the EicC doesn't have coverage, but the reweighting shows the impact in this area. Our suspicion is the parameterization of the PDF itself, because we constrain this area. Due to the parameterization, it also shows some constraint in the lower X region that is not covered by EicC. This is one reason. The other reason could be in the sum rule inside the PDF sets offered by NPDF.
So yeah, that is actually my suspicion as well. I think the parameterization is really stiff, and then basically you have something which is over optimistic in the impact, but especially in the region that you don't cover. Of course, it's more realistic where you cover.
Correct.
Yeah,
Correct.
that's just my comment. Perhaps one can show just the region covered by data, or kind of ask the theorists to release parameters in the parameterization that give more realistic account of. Yeah,
I fully agree. But because of the reweighting, we cannot change the parameterizations of PDF sets.
Oh, right. Yeah, you're right. Okay, so yeah, I mean, I understand now. Thank you very much. Very nice talk. So next speak. We have other questions from Uta and Abe. Sorry, I overlooked this hand. So Uta first. Go ahead.
Yeah. Thank you very much. I think you didn't mention, let's say, what is your goals for the luminosity precision, and for if you plan any forward detector for the precision of the luminosity. So if you go really for cross-section measurements, and what is there your goal for the luminosity precision? Experimental precision to measurement. The measurement.
Yeah. You mean instantaneous luminosity or integrated luminosity?
No, the integrated luminosity that you say, okay, fine, we have then whatever autobahn with 1%, 0.5%, 0.1%. Yeah, that hopefully you will also go to measure cross sections, right?
Yes, and we are thinking it in a different way, because we have various physics topics. Not each topic is measuring cross section. For example, for the helicity and the TMDs and also GPD study, we are measuring the symmetry, right? So now the luminosity. So now how should I say? The systematic is not like what you count in cross-section measurement, right? So
okay, this is fine.
We are thinking in a way that within 1 year or 2 years of running, how much integrated luminosity we have. That's why we reach a number like 50 inverse Finderbar. But of course, with this amount of inverse Finderbar, if you measure cross-section, definitely the systematic error will dominate. But for a symmetry measurement, that's another story.
I tend to disagree, because you need sigma L over sigma T. You need a precise measurement of R. And if you, for instance, like to extract the helicity distributions. So I just like to encourage you to rethink this aspect. Yeah, if I may suggest this. You need sigma L, sigma T. You need a Rosenbluth separation to have a proper R measurement for your kinematic range.
Your comment is on cross-section measurement, I guess.
Yes, and you need this for the asymmetry. Okay, fine. We can also take this offline.
All right. Thank you. So we have a question from Abe. Abe, please.
Hi, thank you. Yeah, I had two questions. One, I think Salvatore already asked about the PDF constraints in the lower X region. But second question was, did you mention positrons ever? Did I miss something?
Positron, not yet. And in the current consideration, we only consider electron colliding with ion beam.
Yeah.
And then there is what I can tell you is there is another discussion about the Super Tau Charm facility in China. Maybe you have heard about it, maybe not. There it is electron and positron collision, and there is a proposal to combine these two facilities in this area. Now occupied by the HEAF facility. And if these two projects are combined, then at the EicC, we will have positron beams. And that's a different story.
Okay, thank you.
Okay, thank you very much again for our speakers. Okay, so we have next speaker, which is Shunzo Kumano. He will talk about possible studies of gluon transversity with the spin-1 deuteron at the hadron-accelerator facilities. Please go ahead whenever you're ready.
Yeah, okay. So I'm not an experimentalist, but I propose as a theorist to investigate gluon transversity at the hadron accelerator facilities. This talk is based on the study with my collaborator, published paper in last year. First, I discuss introductions in general to the spin-1 structure function, and I just briefly mentioned the tensor polarized structure function B1 and then gluon transversity. And this part is already presented by my collaborator in the poster session, so I may skip. Then I summarize my talk. So far, we have been investigating unpolarized and longitudinally polarized and some other structure functions. But however, the tensor polarized structure function B1 has not been investigated very extensively. For measuring B1, we have to use the polarized spin-1 target or beam. A typical example is the deuteron. In the pattern model, this B1 is expressed by the tensor polarized pattern distribution function. This is the unpolarized quark distribution in the polarized deuteron. So it's very different from the longitudinally polarized pattern distribution function you are aware. And nucleon spin, we have been investigating for many years for finding the origin of nucleon spin. And on the other hand, the deuteron structure is also interesting, as I show in the possibly next slide. So far, our theoretical expectation is very different from the existing measurements. So as we had the nucleon spin puzzle, we may also have a tensor structure puzzle. The reason is that these are the Hermes measurement. This is B1 versus the Bioken X. These are measurement, and based on our composition picture, like this one, we can calculate that the B1 of the deuteron. And this is our expectation at the average Q-square value for the Hermes collaboration. So this tendency is very different from the experimental measurement. So we may have some kind of difference between the experiment and theoretical expectation. And the gluon transversity is another interesting observable which I discussed today. For measuring quark transversity, you have been investigating several years. On the other hand, the gluon transversity has never been observed experimentally. For measuring the gluon transversity, we need to have a target with spin more than 1, because this helicity flip of unit of 2 is necessary. So for the nucleon, of course, this is not possible. So it doesn't exist in the spin 1/2 nucleon. On the other hand, this fact indicates an interesting possibility. this proton neutron do not contribute directly to this gluon transversity. So if a finite distribution is found, it is physics beyond this simple binding picture. That's why we are interested in this gluon transversity. And this gluon transversity discussed in our paper, and also this will be in print in the Progress in Nuclear and Particle Physics. It's the NICA project. They are interested in deuteron polarization. So gluon transversity, this is already I discussed, so I may skip. And for the notation, there are various notation because there is almost no, only a few or several papers on the gluon transversity. For measuring the gluon transversity, we need to have linear polarization of the deuteron. It is a part of tensor polarization. And this gluon transversity is defined in the linearly polarized deuteron, and the gluon polarization direction is x direction minus y direction. So it's a little bit complicated observable. So and the notation is also confusing. Almost everyone uses different notations, so you may be careful about reading past paper. In our notation is delta t g. So, but all of these are essentially the same. And there are almost no paper, unfortunately, for the physics mechanism. So far, I found this very old paper by Nazar and Footboy. They consider as deuteron as a bound state, usual bound state of proton neutron. And in addition, there may be a delta data component. Then there is no contribution directly from proton neutron. So this kind of delta contribution could give rise to finite distribution. Of course, this is not the only mechanism you may see to find the finite distribution. So if you have an interesting idea as a theorist, you may propose. And so far, there is only one experimental consideration, which was submitted as a letter of intent a few years ago. They use polarized deuteron, and of course, this is a very simple cross section in the scaling limit. So there should be maybe other corrections. But in any case, if we look at the cross section as the function of this polarization, azimuthal angle of this polarization, then this term is extracted from the experiment, which is directly proportional. Of course, this is the integral, but it's proportional to the gluon transversity. And so they try to measure this quantity in the middle of 2020, as soon as the deuteron target is prepared. But however, the purpose is, theoretical purpose is that we are interested in proposing to do this experiment at the hadron facility like Fermilab, NICA, or somewhere else. And it's as a complementary project. And in this paper last year, we proposed the proton-deuteron Dorian process of, mainly considering the Fermilab E1039, so-called spin quest. But however, this project is also possible at NICA facility. And for deriving the cross section, we discussed this cross section is given by the Parton distribution function. This is a Parton distribution function in the proton. This is proton deuteron Young. So this is the proton part. This B is the deuteron part. So and what we found is that if proton is linearly polarized and the proton is unpolarized, this combination survive in the cross section, and it is possible. I'm sorry, this is also defined notation for the gluon transversity. And what we found is that if we take the linear polarization of the deuteron, the cross section is proportional to the unpolarized Cope distribution in the proton multiplied by this gluon transversity. So it is in principle, since this is very well known, it is possible to extract this gluon transversity from the cross-section measurement. And we estimated this cross-section as a function of dimuon mass, and also this spin asymmetry. It's relatively small. It's like typically few %. And then this theoretical value is even overestimation, because there is no gluon transversity. So we just use longitudinally polarized distribution. So it may be an overestimation. But in any case, this is our first estimate. And Dustin Keller was wrote proposal even last year, and unfortunately, the Bryngemark was not held last year, so he's thinking about submitting this year for this proposal. And this is about linear polarization of the deuteron, and it's a little bit complicated. For example, if one use usual transverse polarization, various factors contribute. In addition to the usual transverse polarization, we have SLL, means the tensor polarization, and also this is the about linear polarization. So even in the linear polarization, it contains the part of the tensor polarization SLL. So we have to subtract out these two to cancel out this one and try to obtain this linear. STT is gluon transversity, is related to gluon transversity. So it's a slightly complicated spin observable, but hopefully it will be done experimentally. And in future, there are familiar people, experimentalists. We propose this experiment this year, hopefully this year. And NICA project, they're interested in this deuteron polarization. So it may not be that very young, but they are interested in this gluon transversity. Of course, this will be done at Zhao, and we continue to EIC and probably Chinese EIC, hopefully. And the firmware, of course, there is approval experiment, firmware E1039 for the polarized proton, but they are also interested in the deuteron polarization, and right now the transverse structure deuteron is also considered. And the NICA facility, they are building this facility with the polarized proton and polarized deuteron. And I also heard that polarized proton deuteron collision is also possible.
We have 3 minutes.
Okay. And I'm finishing. So, and this part, and we also studied the TMD for spin 1 hadron. So the TMD part could also be investigated, but this is already presented by in other poster sessions. And the TMDs for spin-on hadrons, there are new structure functions in addition to the usual ones for the proton. These are the are studied by Murat a long time ago. But the new structure function we proposed this year are these new structure function, twist 3, and also, oh, I didn't show twist 3 and twist 4. And we will propose new sum rule also, Himmel cutting. So I finished this one. The gluon transversity is an interesting quantity, and it will be measured at the Fermi zero, and it will be proposed at the Fermi. So this quantity is very interesting for exotic component in nuclear beyond the simple bond state of a nucleon. So, and there are various accelerator possibility to measure this quantity. So hopefully experimentalists are interested in this quantity. It has not been measured at all. Okay, yeah, I think that's all. That's all. Thank you very much.
Thank you very much. So questions for our speaker? No questions? Okay, very clear talk. Thank you very much again.
Okay, thank you very much.
So our last speaker today is Lene, Kristian, Bryngemark, that will talk about the light dark matter experiment.
Yes.
Whenever you can.
Yes, so just exactly. We'll share my screen. Can you still see my slides?
It's buffering something. I only see loading.
I see. Okay. Now
yes.
I'll try full screen again. It does not work. Okay.
Yeah, it works. It works.
It works with full screen?
Yeah, it was working with full screen. Yes. Perfect. Thank you.
Wonderful. Okay. Right. So I will close this session, very diverse session, with a talk about probing sub-GeV dark matter with the light dark matter experiment. So consider that the present day dark matter abundance is basically a freeze-out relic from the hot early universe, where you have dark matter like this that annihilates into standard model particles, and at some point that stops, and you have a relic abundance of dark matter. This is realizable with rather minimal assumptions on the dark matter itself.
Lene, sorry for interrupting you. We see your slide 4. Is it what you are talking?
Okay, let me just give up full screen, and I think this should work, right? Now you see my second slide. Is that it?
Correct. Yes.
Okay, so let's do that. Right. So if we just make the requirement that we want to see dark matter at all, it should be observable. Then we have to have some minimum non-gravitational interaction by which to find it in experiments. And if we do have that, then it's kind of hard to avoid having thermal equilibrium at some point, as long as the interaction rates exceed the Hubble expansion rate. And what you see here in this graph is this kind of point where the interaction freezes out. So this neatly predicts a minimum interaction strength, which is very good for an experimentalist because that gives you a sensitivity target, and simultaneously it constrains the feasible mass range that you look for. So if you are looking for lighter mediators like in the sub-GeV regime, you also have to have a non-standard model force, which is weaker than the weak interaction. So this is like kind of the dark sector paradigm. Okay. It really is not very nice if my if my overlays are not working. I really want this to work. I'm so sorry. Just give me another second. So let me try this in the opposite order. Full screen first and sharing then afterwards. Let's see if that works. No, it does not.
Oh, it's out again.
Yes, I can see that. Did this help? You see my slide?
Yes, we do. Yeah, in full screen.
Fantastic. Okay.
And they changed different slides, so it works.
Oh, wonderful. Thank you so much. Okay, so then we continue. So the simplest possible dark sector extension that you can imagine, perhaps, is dark QED, which then mixes with standard model QED with this mixing parameter epsilon here, and you can create a reasonably feeble interaction that way. And this Feynman diagram can rotate in different directions depending on how you want to detect this process, but here we're focusing on the accelerator-based angle. And very nicely, if you look at the kind of the interaction strength versus dark matter masses, all the different thermal prediction targets all line up very nicely within this range that is not fully yet excluded. So this is a plot with historical experiments which have excluded lots of the parameter space, but there's still a window of opportunity here in the sub-GeV regime. So LDMX is an accelerator-based fixed target missing momentum experiment, which focuses on escaping dark matter, first order at least. Our hope is to produce massive dark photons, or A primes, through Bremsstrahlung in a thin target. So this is what's shown here. And we focus on the recoiling electron, so we're rather agnostic when it comes to exactly for producing dark matter or an A prime, which then decays to dark matter. The strategy we have is to make our detector sensitive enough to have basically all the standard model backgrounds appear in it. These are produced in the typical Bremsstrahlung process. And then we veto everything except for low activity events, which is then our signal-like signature. The kinematics are shown here on the right, where you see that the A prime carries most of the beam energy, and the recoil electron, which is light, gets a momentum kick because something massive was radiated, and it thus gets a large deflection angle here. So this is a missing momentum experiment. But I also want to note that already the recoil energy distribution is quite different between the standard model processes here, where the electron carries most of the beam energy, and the different dark matter, dark photon mass points here, where they all peak at low fraction of the beam energy. So LDMX will be built at SLAC using the LCLS2 beam, which is an electron beam for photon science. The goal is, or the aim is, to steal some of the electrons here with Lene down to end station A, where we will build LDMX. The beam energy is in a good regime for us. It's a 4 GeV beam that can be upgraded to 8 GeV later on, which will allow us to probe higher mediator masses. And it's low current, which means that we will be able to measure each incoming and outgoing electron, connect the two, so we can get the missing momentum measurement in order. The repetition rate of this beam will be high enough for us to be able to collect the needed 10 to the 14 electrons on target in a matter of a couple of years. So right now we are in the R&D phase, and in a couple of years we will start construction. That's the plan. The detector concept here in not very to scale sketch. The beam enters from the left here. You can see the incoming electron track or trajectory curving in the dipole magnet that surrounds the tagging tracker. The tagging tracker is laid out to follow the trajectory of a 4 GeV beam electron. Then there is a 0.1 radiation lengths tungsten target, where we hope to produce the dark matter. Behind the target, we have a recoil tracker to follow the trajectory of the recoiling electron, and then we have calorimeters, an electromagnetic and an electronic calorimeter to measure the energy. The backgrounds are really what shape the requirements on the detector, and I'll walk you through this kind of sketch of the increasingly rare different processes that can occur when an electron hits the target. So a common process would be to have photon Bremsstrahlung, where you can measure the electromagnetic shower of the photon in the electromagnetic calorimeter. There can also be E plus E minus production, where you would have showers plus additional tracks in the tracker, so you can veto that. If you have high enough energy photons, you can start to see hadrons, and you would catch them in the hadronic calorimeter, and also anything charged in the electromagnetic calorimeter. If you have high enough energy for muon pair production and a really high granularity electromagnetic calorimeter, you can actually start seeing tracks in the calorimeter, MIP tracks. This is what we hope to do. Kaons will similarly also produce tracks and also additional decay activity in the calorimeters. And it turns out that the hardest process for us to veto on is probably this one, where you have a photon producing a single neutral hadron that could escape your HCal if you don't make it deep enough. So this really shapes the requirements on the HCal, because if it escapes, it looks just like the dark matter signature, basically. So this is one of the processes that we have been focusing a lot of our vetoes on handling. So the detectors then pre-targets are all about knowing what's coming in. So first of all, there is a trigger level electron counting system with which provides the inputs to the missing energy trigger that we use. It has 3 arrays of horizontal scintillating bars, like shown in this picture, and it's positioned on different places along the beam. Then there is a tagging tracker, which is there to tag beam electrons offline. So it has to measure both the momentum and the impact parameter of electrons. It does this with 7 stereo layers of silicon strip modules. They are spread out a little bit, and they are vertically oriented strips, such that we get optimal momentum resolution in the bending of the track. Then behind the target, there is a second iteration of tracker with basically the same technology, but the layout has been optimized for good momentum resolution and acceptance at 1 to 2 GeV, which is slightly lower than the beam energy. Then we have the electromagnetic calorimeter, which is high granularity. It's based on the CMS high granularity calorimeter upgrade. And you can see this figure stolen from CMS where muon clearly produces a MIP track in these layers. So we have in total 34 layers of that, and it's silicon, tungsten, and radiation hard. Then finally, there is an hadronic calorimeter that is laid out on all sides of and behind the ECAL. So it has wide and deep coverage. It's a sampling calorimeter the steel absorbers and scintillator bars that are in alternating X and Y orientation, such that we get some spatial resolution out of it. Then on to the event selection and the vetoes. So I remind you that the goal is to go to basically 0 background from 10 to the 14 electrons on target, which is quite hard. So I'll walk you through this, mostly focusing on the most challenging background here, which is, again, photonuclear interactions in the ECAL. So the first handle is to deal with the recoiling electron and look at the ECAL. So we trigger on anything ECAL energy is less than 1.5 GeV. And we also don't want any additional tracks being produced, and the electron momentum has to be less than 1.2 GeV. So that's a trigger. And there we can already go down 6 orders of magnitude in events. Then the next part is to exploit the high granularity ECAL features. So we have the main working horse is a BDT that has been trained to reject photonuclear events in the ECAL. You can see this, the rock curves here, where you have pretty high efficiency for signal at different mass points, while the rejection is very good, the very low efficiency for background. So this goes down to about another 3 orders of magnitude. Then, as I mentioned, there is also MIP tracking, which is very powerful on sparse events, which would not probably be picked up by the BDT. But before we apply that, we veto on the HCAL activity, and it's a really stringent cut on just allowing only a few photoelectrons from this rather big calorimeter, which we have made big such that we will catch even single neutrons. And when we apply that cut, we go down to about 10 events. And then applying MIP tracking on them, we get down to the desired rejection power. So I've been saying that this is a missing momentum experiment rather than missing energy, but the only information we have used so far is ECAL energy and the shower shapes of features in the ECAL, track multiplicity, and HCAL activity. And we have not touched the recoil electron transverse momentum yet. And this is really on purpose. We want to keep it available to reject any surviving backgrounds after we have been optimizing all of this in simulation. And also it can be used to constrain or characterize the signal. And this is what I show in this graph here, where you can see the kind of standard model background recoil electron PT in black, which is very steeply falling. And then there is a wide distribution of electron PT for the different signal mass points. And it gets to higher and higher PT with higher masses of the radiated object. So there's a correlation there that we want to exploit. For the expected sensitivity, shown here on kind of the same graph as before, I show that the blue line is the phase 1, the 4 GeV, 1 to 2 years of running, and then the full after phase 2, we kind of exclude most of the available thermal model phase space up to at least a few hundred MeVs. I also want to point out, though, that we expect some sensitivity to visible signatures as well. Here is one example where there is a displaced visible decay and a strongly interacting dark sector. It's a slightly more complicated and indirect dark matter depletion mechanism, but the key here is, again, that the A prime decays to hidden sector pions, different ways which carry away some momentum. And then there can also be a displaced lepton pair produced. So if you focus on the missing momentum part of it, you get this exclusion curve here. And if you are also able to reconstruct displaced decays, you can get this purple line here. So in summary, thermal relic models for dark matter offer a predictive and compelling explanation, and LDMX is being designed to conclusively probe the sub-GeV mass range for these models. It's a missing momentum experiment. It focuses on invisible signatures, and it has sensitivity also to displaced visible decays. So we are getting closer to the construction phase now, so we're, of course, all very excited about this. Thanks.
Thank you very much, Lene. Okay, questions? Since there are none, so maybe it's getting late. So thank you very much again. And I would like to take this opportunity to thank all our speakers today, and very nice and very, very diverse session, as it was said. So thank you very much and see you tomorrow. Bye-bye.
Yeah, see you tomorrow. Thank you all. Bye-bye.
Bye-bye.